So thanks for having me virtually. It's exciting to be a part of the process and talk with all of you, and I hope the product of everything is great. I'm going to talk about some ideas around model building in dark sectors today, and to the extent that I discuss anything that is work that I've done, it's going to be really work done by these people here below, and I'll emphasize that as we go. So you can't give a Snowmass talk without drawing this triangle to say that there's the cosmic frontier, the energy frontier, and the intensity frontier, and there's relationships between the two of them, between, for instance, cosmic and energy, between intensity and cosmic, between intensity and energy, and all these connections are extremely well known. But for us, there's also important to emphasize that our purpose here is to be at the theory frontier. And we sort of can group many of the issues that we had on the previous slide into the experimental frontier. And although I think that we, the theorists, are the real beneficiaries of it, it is more symbiotic than just a one-way street. So models, the new models and new ideas we have can provide to data, to the experimental frontier, new analyses with data they have, and to motivate new experiments that can be piggybacking on or totally new, such as, just to throw an example, the phasor experiment. And of course, we, in return, get signals to explain. We get understandings of we get ideas of sensitivity of what our models can be constrained by, and sometimes motivation to think about new directions in models. And what's especially exciting for me at the moment, and I think for many people at the moment, is that we are in this era of precision cosmology that has long been anticipated. And we often point to something like Planck and the TT and EE spectra of Planck as giving us some fundamental grips on what's going on in cosmology, but that's just a small part of it. You have other studies like ACT and SPT of the CMB. You have incredible studies of lensing. You have new surveys. You have Gaia. You have sources of data and experimental results across scales and times like we have never before had. And as a consequence, that means that we have the ability to start really talking actively about the dark universe. So the other requisite slide that we always show when we're talking about cosmology is this one, where we say, look, here's dark energy, here's dark matter. They're very important. You can see they're important because they're such a big fraction of the universe. But if we are thinking about cosmology and wanting to understand the universe, it's not just a question about how big a slice of the pie is today, because the universe has been around for a long time. And so if you, for instance, just slide your time back to a redshift of about 30,000, the picture looks very, very different. Photons are the dominant picture. And as far as the dark universe goes, neutrinos are actually taking over and beating out dark energy and dark matter as the most important dark sector particles to understand. And so while we've spent a lot of time, with good reason, trying to understand dark matter and dark energy, it's also worth understanding these neutrinos, because although we expect there to be neutrinos there, at this point, that's just a supposition. Really, we just know that there is dark radiation there, and it's an open question what that is and what its properties are. Although neutrinos are, of course, the clear, obvious explanation. So why is this a special time to think about models and think about models of the dark universe? Well, the way I think about it is something like this. We have all the scientists who are out there trying to look for dark matter. And the thing about dark matter is that it is something which is not us. It is something different from us. And not only is it different from us, it is somehow distant from us in some meaningful way. And when it tries to communicate with us, there's always some sort of barrier to that communication that makes it hard to totally get. And that when it does communicate with us, in at least many models of the dark universe, it can't even directly communicate with us. It has to communicate with us through some sort of medium that maybe we aren't as used to. So I would say that we're not really just looking for the dark matter. We are actually looking for socially distant matter. And this is the best time where we are in the mindset to really look for something like that. But of course, I'm kidding. That's not the only reason why now is a special time. What's special about this time is also what's going on with data. So we've just come out of this unprecedented era of new wavelengths and messengers. So for instance, gamma rays, we had egret that matured into Fermi and gave us this incredible gamma ray view on the sky. We've had evolution of charged cosmic rays, for instance, from Pamela into AMS, and our understanding of the microwave sky from WMAP into Planck, where we now have very clear views, mature views on these different aspects of viewing the universe that we didn't have before. And we're entering into a new era, for instance, in terms of surveys, where before we've had large-scale surveys such as SDSS, but we're going to move into LSST or Rubin. We had Hipparcos, which we're now is evolving into something Gaia, where it's a full sky map, going to new scales with the CMB, and brand new technologies such as gravity waves and radio arrays, which we have recently heard some about. And the question isn't just what kinds of ways can we test our models with these new technologies, but it's also what kinds of things could be tested with these. Because what we really want to be thinking about is not just how can we use these new technologies to test our favorite candidates out there, but what kinds of candidates could be out there that maybe we didn't have a chance to test, but now we can. Now, to that end, I would emphasize that neutrinos are special. So this idea that we should be thinking about the dark radiation is that it's not. And although it must, we know neutrinos are out there, we know they would have been populated in the early universe, they're also very, very special in being the only standard model singlets that really stick around in the universe. Okay, photons, yada, yada. But so even though they interact with W and Z bosons, because those gauge symmetries are broken, they're effectively singlets in the low energy theory. And that means that although they maybe contain a lepton number, they have the ability to mix with other neutral particles out in the universe and thus pick up the properties of those neutral particles. So for instance, here is just a very, very simple example of how something like this could work. You imagine that you start off with, a neutrino, and it marries some Dirac right-handed neutrino, and then that's going to cause the neutrino and the right-handed neutrino to mix with a mixing angle, which is just a ratio of mass scales. But let's suppose that out there in the universe, in the Lagrangian of the universe, there's some other particle, not unlike the neutrino in that it has been charged under some gauge symmetry. That gauge symmetry has been broken, and so it too can mix with a neutral particle. So there is some other particle out there, psi. Psi also mixes with the N in precisely the same way, with some mixing angle theta 2, which is also a ratio of mass scales. Well, when you go down to the low energy theory and you look at the actual massless state that persists, the thing that should be filling the universe that we see today, that massless state then picks up some very, very small charge under this new weak gauge boson, and in a way that could be very, very hidden from any experiment so far. And so in this way, because the neutrino is a standard model singlet, it gets access to these sorts of gauge forces in a way that other particles do not. So you could imagine a non-lambda CDM history where at high temperatures, everything looks totally normal, but then at late time, through some very, very, very small coupling, the neutrino can annihilate into dark gauge bosons and freeze in this additional sector of particles at a very, very late time. So you could have an interacting fluid of neutrinos and dark gauge bosons populating the universe and have never shown any sort of sign of that in the early universe, and it only shows up in the late universe. And so something like that would be a prime candidate to think about as something that could be tested by this new era of precision cosmology. So let me take a step back and just say, I want to talk for a moment about anomalies. Now, as we know, when you push any search far enough, you will encounter anomalies in those data. And these can be for a wide variety of reasons. You can have events that you didn't model appropriately. You can have unexpected systematic errors, but you also can have actual new physics. And the example that I would like to point to is the solar neutrino anomaly, which was a very persistent anomaly of great debate for a great deal of time before it ultimately bore out that there were, in fact, masses in an unexpected fashion for the neutrinos. So anomalies, whether or not they end up giving us new physics or not, have been long a fruitful source of new ideas for model building, not just because they're a question to be answered, but because they are typically lying at the edge of what we can do experimentally. And so they are giving us an insight into the types of models that can be tested by advances in those same experiments over the next several years. So one that's especially exciting, I think, for model building right now is the Hubble tension, the H0 tension. So Many of you have probably heard of this, but for those people who have not, let me just very quickly summarize it. So when you look at the CMB, the cosmic microwave background, and you look at, say, the peaks in the multipoles, there are many, many peaks, many properties, how that falls off, and there are many parameters that go into that. And one of them is the expansion rate of the universe today, h0. And when you fit to the early universe, when you fit to the CMB, you come up with this value of h0 of 67.4 kilometers per second per megaparsec, or just 67.4. On the other hand, you can actually go out and measure the expansion rate of the universe. And this has been done by many groups, but probably with the highest claims accuracy by groups working with supernova. And when they go out and they measure the Hubble parameter, they come up with this value of 73.2. So there's a clear many sigma, now it's 5 sigma officially, discrepancy between the supernova data that measure Hubble locally and the CMB data that measure it from the CMB. And it's not just one experiment. There are many, many experiments that show this. Of course, there are systematics and there are issues, and I'm not going to go into them. But I think it's safe to say that this is a fairly robust anomaly that is worthy of thinking about, and it may or may not bear out to be new physics or not, but there's certainly something to be understood. Now, people have argued, and the reason why this is especially relevant for thinking about dark radiation and dark physics around in the early universe is because people have pointed out that this is really, in many ways, a problem of the horizon. So simplifying this to an order which is beyond which is appropriate, the location of this first peak is basically given by the angular diameter distance, of the angular size of the sound horizon at the surface of last scattering. So you had some wave that could propagate some distance. So this is the distance that that wave can propagate at the last scattering surface. And then we look at it from here, and that wave has some angular size. And that angular size is just this ratio, basically, of this distance over here and the distance to the surface of last scattering. So you really just have to know those two numbers in order to calculate where this peak should be. And the physics of this is fairly straightforward. The sound horizon is an integral of the speed of sound divided by the Hubble parameter in the early universe. And the angular diameter distance is just the integral of dz over the Hubble parameter. But what's important to note is that the sound horizon is basically dominated by the Hubble constant at recombination, and the angular diameter distance is dominated by the Hubble distance, the Hubble parameter today. So this quantity theta is really just the ratio of those two scales, which means it's really just the ratio of those two Hubble constants, more or less. So if you say that I go out with the CMB and I measure the Hubble constant to be 67, that's because I assume that I know what the Hubble constant in the early universe is. If I know the Hubble constant in the early universe, then I know the denominator, which means I can figure out the numerator if I've measured this hand side over here. But if the horizon was different then, if somehow the Hubble constant was different from in the standard model, then that would tell me that the numerator should be different too. And this is something that has been pointed out by many people for many years. Here's a plot from recent collaborators all the way back in 2016, where there was already a tension starting to appear, where they pointed out that, look, if you take the Hubble parameter and you fit it with some free additional number of degrees of freedom, relativistic degrees of freedom, the parameter h0 will shift up and to the right. So as you increase the number of relativistic degrees of freedom, you will also have a higher value of h0, just because those additional relativistic degrees of freedom are heating up the universe back then and causing the universe to expand faster. But I said I was oversimplifying, and I was, because as soon as you start messing with that first peak, you start messing with everything. You increase silk damping and other properties that are measured in the CMB, and you can't just dial up an effective without having it show up other places. So you need to control all of your knobs, and hopefully you can find a fit. And in a really wonderful paper by Pernal Verde and Rees in 2016, pointed out that actually when you consistently try to do this and increase the number of effective degrees of freedom, you find out that that if you actually include the full fit of Planck data out there, you actually find that you're constrained to live in a region which is not consistent with this high value of H naught, because largely it's changing the silk damping. People followed up and said, well, look, we're model builders, right? We're particle theorists. We shouldn't just imagine if you're going to increase an effective, that's not just adding neutrinos, that means you could be adding new physics there. And we should think actively about what that physics could be. And one thing that it could be is that you're actually causing that fluid to be interacting. So in a very nice paper in 2019, Kreisch, Siracine, and Doré studied this, for instance, and showed that there was a tremendous amount of freedom to compensate for these additional degrees of freedom if instead of having a free streaming fluid, that fluid had its own interactions that could change the silk damping by increasing clustering at small scales. So that was an idea as well. But it turns out that this can give you somewhat of a fit, but still not a perfect fit. And that when you actually try to put it to a test in the data, it's still a tension at more than 3 sigma. But that's not my point that I want to focus on. The point what I want to focus on is, let's suppose you're a particle physicist, as most of us are, and you said, I want to imagine an interacting radiation fluid in the early universe. Well, what does that mean? Well, for instance, that could mean that I have a fermion field psi, and I have some scalar field phi, and they have some Yukawa coupling here, some sort of interaction. And that's the interaction. So I've got the universe full of psi and phi, and they're interacting with each other and scattering off of each other through some Yukawa coupling. It's a totally simple and reasonable model. But we also know that as soon as you include a scalar field in your theory, you know that there should be a cutoff. There should be a mass there for that. What's controlling that? Where did that go? And what's the effect of that mass, right? We can't just write down a scalar field and walk away as though it doesn't do anything. So if you want this fluid to actually be interacting, strongly interacting during the time of the CMB, you need the mass to be lighter than about an MeV for order 1 coupling. So that's a pretty light scalar field. Now, I don't know about you, but the trick that I always do if I want to understand how to keep things light, and again, this is a theory talk, is to say, well, let's just imagine that we can embed this into a supersymmetric theory and to see how that works. And indeed, the field content of 1 scalar and 1 fermion is precisely the amount to fill out 1 chiral superfield, and it can give you then the simplest interacting supersymmetric model, namely the Wess-Zumino model, where you have a superpotential with 1 term in it that contains both of these fields. So you would expect there to be some SUSY breaking, and so this scalar should have some mass. But if the SUSY breaking scale is, say, for instance, 100 TeV, then the scale of the mass breaking that you would expect is around an EV. Okay. So what's my point here? My point here is just to say that we can talk about interacting radiation, or we can talk about free streaming radiation, but it's nice to sort of take that idea and say, well, what is this for real as a particle physics model? And what are the implications of taking that seriously as a particle physics model? And one of the implications is that there should be a mass for this scalar, and that mass for that scalar is naturally in the range where it would be relevant for understanding and affecting the CMB. So this would be what we would call a natural model from a particle physics point of view.
So you have about 2 minutes left.
Okay,
2 minutes
I
left.
can't hear you. You're breaking up, but I think I understood. Thanks. Yeah. So the consequence of this mass is actually very, very interesting. And so something that you think that you learned from Kolben-Turner, I thought that I learned from Kolben-Turner, but turns out I had not learned from Kolben-Turner, is the effect of going through a mass threshold in equilibrium. So we all have read it, we all think that we understand it, and maybe some of you do, but probably some of you don't, so I will tell you. So imagine that you're at a high temperature above a KeV. So you have a field which is proportional to T⁴ with some number of degrees of freedom. And then the universe cools down, cools down, cools down, cools down. And eventually you get to the mass of phi, and all those phi particles go away. And they inject all of their energy and entropy into the psi particles, and phi is gone. Entropy is conserved, and so psi heats up. And this is sort of something that we all learned because this is what happens with neutrinos and photons and electrons, right? Electrons annihilate away, they heat up the photons, and now the photons have a temperature which is a factor of 11/4 to the 1/3 power, which is higher than the temperature of the neutrinos. But the thing that we don't teach when we teach this in Kolben-Turner is that you have actually increased the amount of energy density in the photon fluid above what it would have been if it had just been redshifting smoothly. And by photon fluid, I mean photon plus electron fluid. So you think that you're going along, you've got some energy density in the fluid, in this fluid, and you're comparing it to the stuff that some other fluid that's out there, like photons, and it's coming along, and then you get to this mass threshold, and when the entropy gets shifted, the actual energy density in that fluid goes up. So in effect, what you have is sort of the number of effective degrees of freedom at early times and the number of effective degrees of freedom at late times are different, and they go up. So this is what we mean when we talk about a stepped fluid, that you start down here at 0.5, for instance, as the additional degrees of freedom, then you go through this mass threshold and the effective number of degrees of freedom that you have goes up. And if this is happening during the CMB, you can actually study this, and it tends to shift the peaks of the CMB, whatever. You can do some big, very complicated analysis, which we did, and you find that when you include the shoes data, the theory wants to have an additional amount of interacting radiation, and it actually wants to have a transition. It wants to have a mass threshold. The CMB data alone actually want to have some sort of a mass threshold in it at a redshift of around 30,000. So just the summary of that is that there is a mild preference in the CMB for not only dark radiation, but dark radiation with a mass threshold in it. And this is different because without a mass threshold, without shoes or anything like that, there's not any evidence for additional radiation. So you could get very excited, and I could get very excited. I could say, is this the solution to the H0 tension? And I would say that it doesn't matter. And then I would say, well, okay, it does matter, but that's not my point, right? The point is that we can have a conversation about whether there is a mass threshold in a small fraction of the dark radiation present 13.7 billion years ago. And that's the era we are in. And that's the era we're going into, where you can talk about these sorts of questions quantitatively, and they have meaningful impacts on the data that we actually observe. So the speculation that I would have from a model building point of view is if you think back to the last, say, 10 years of dark matter model building, where we went through many, many questions about dissipative dark matter, warm dark matter, fuzzy dark matter, studying the consequences of them and studying the implications of them for actual data, I think that we're going to enter into an era, we're going to go through a similar set of discussions, but about dark radiation, especially as higher multipole data in the CMB come in from ACT, from Simons and Bird Observatory, from CMBS4. We are going to be able to talk quantitatively about models and whether they have experimental consequences that could be talked about and studied. And that makes it an incredibly exciting time to be developing models like this. And I've shown you one type, but there are others: early dark energy, the Myron explanation of neutrino masses, and many, many, many more that can come in and show you models that can have an implication in this period. But I still believe that we have really just scratched the surface of the types of models that could be relevant for this new upcoming data set. So this is just some small step, the discussion that we're having here. But I'll conclude to say that the era of precision cosmology is allowing us to ask detailed questions about the dark sector in a way that we could not before, in the way that we could only dream of, really. And that dark radiation, like dark matter, is there. And we really believe that it's neutrinos, but we should be really scientists about this, because neutrinos are special. They could actually thermalize a dark sector, or other sectors could be piggybacking around the neutrinos. And so we really need to study this as critically as we can. And the H0 tension, personally, it's exciting enough to me to think about how new models could affect it, because it's something clear that we can talk about and we will make progress on in the near term. And this is one example of a model that could give you something that could explain it. But regardless of what model it is or what happens with H0, the upcoming data is going to allow us to ask questions about models of this dark sector in a way that we never could before. So thank you very much.
All right, thank you for this really, really nice and entertaining talk. Are there questions in the room? We have a little bit of time. Yes, Lance.
Hi, Neal. Lance Dixon. Thanks a lot for this talk. How about the BAO, the baryon acoustic oscillation data? I think it's consistent with Planck, but maybe you'll tell me it's basically just remeasuring the same thing, even though the light comes from relatively low Z. Is that the case, or how is it affected by a dark
Yeah,
radiation?
I'm going to tell you that that's the case.
Okay.
I'm going to tell you that that's basically the same, because BAO is also essentially a measurement of the sound horizon at something like the surface of last scattering, right? So it's essentially measuring a similar ratio. So that surface divided by some distance to wherever you're measuring the BAO feature, which is then set by the current H naught. So if you believe that that physical distance scale, what's setting that standard ruler, is the sound horizon in the early universe, but you assume that sound horizon is set by the standard model when it's not, then you will change that in precisely the same way that you change it for the CMB. So effectively, you're measuring something like the sound horizon times the local Hubble scale is effectively the same parameter that's getting measured by both of these experiments. And so if you change one, then you tend to change the other, and they should be consistent. If you have some physics that changes the sound horizon in the early universe, then it should have a similar impact on the BAO measurements and on CMB. So they should still line up and be consistent for this reason.
Thanks, Neal.
So any more questions in the room? Any virtual questions? Oh, there's one comment. Yes. Dan.
It's Dan Green. I just wanted to make a small comment. So in advertising this sort of perspective, I think that to add to Lance's point, the BAO is really important, because without it, you're not going to measure. That's what measures neutrino mass in cosmology, and also CMB lensing. So there's a really much more you can do really cool stuff with the neutrino sector, but it really covers a much broader redshift range. It's not just at Z of 1100 or 3000, but it really incorporates data that covers like all of redshifts from here to the CMB.
Yeah, and I totally would agree with Dan on that. And I want to emphasize that when I was saying that it was similar to the CMB, I meant with just regard to this one question about when people talk about the H naught measurements from the BAO. It has a tremendous amount of data that you can do and analyses you can do with BAO that are beyond that.
All right, I think we should probably move on. So let's thank Neal again.